in the country. Please make sure that you follow the instructions given by the authorities and stay at your homes. Anyway, your education must continue. So your meeting, and we are going to start the routing protocols. Now we are starting a chapter on routing. Now if you can remember, we discussed about switching. When we had the lectures, we talked about two vital factors of switching, which is two protocols actually. So under switching, we discussed about VTP, VLAN trunking protocol, and we talked about STP, spanning tree protocol. Now we are moving away from layer 2, which is switching, to layer 3, which is the network layer. And in network layer, the main device is router. So in order for router to work, we need routing protocols. So we are going to discuss about routing protocols which are used in today's routers, and also what are the mechanisms. So our topic today is distant vector routing protocols. Now what is distant and what is vector? But before that, let's look at the objectives. After you complete this chapter, you need to be able to identify the characteristics of distant vector routing protocols. You need to describe the network discovery process of a distant vector routing protocol such as RIP, and then you need to describe the process to maintain accurate routing tables, how the routers are basically managing these tables, and you need to understand what's a problem called routing loop and how we can prevent those, and the modern routing distant vector routing protocols used in today. So distance vector, distance means direction, and basically the distance to the final destination. When I say destination, it's between two routers. Now one router can be in your home, that's your home router, and your home router transfers data from your PC to the ISP. So next router from your home will be the ISP router. So the distance between these two will be considered as the distance in the distant vector routing protocols. Vector means the direction, where the traffic should flow, where the traffic should be directed. So distant vector routing protocols basically talked about two things: where should I send data and to which direction should I send data. These are the two things that routers are worrying about. So we are talking about three main routing protocols, actually four to be exact. We are talking about a routing protocol called RIP, stand for Router Information Protocol, not for STPs, but you can remember in any way. But in these days, RIP is commonly used for STPs, but this is for Routing Information Protocol. And then we have something called Cisco, which is a Cisco proprietary protocol. It's called EIGRP, stand for Interior Gateway Routing Protocol. And we have another one from Cisco, which is EIGRP, the newest version, which is Enhanced Interior Gateway Routing Protocol. And we have the IEEE Routing Protocol RIP version 2. So we are basically talking about four main protocols here. Now there are some characteristics that you need to understand about a distant vector routing protocol. Now before we talk about this, I want you to focus on the diagram given. So you can see there are four routers. Each and every router should update their neighbors on the routing update. These are known as routing updates. Now each router maintains something called the routing table. We will discuss about the routing table in a bit, but for now understand, each router has to discuss about this routing table or share this information about the routing table with each other. So a distant vector routing protocol sends this update periodically. That means every once in a while they will send this update to the neighbors. And these are broadcast updates. That means it will be sent to everyone. All the neighbors, all the paths will be flooded with the update. And you send in the entire routing table along with this update. You are not sending partial information, you are sending the entire routing table. Now look at this diagram. For example, we have two routers, router 1 and router 2. In R1 you have a LAN connected, so this is a LAN. We have 172.168.1.0/24, and we have a WAN between these routers which uses 172.168.2.0/24, and we have another LAN for the R2 which is 172.168.3.0. Now if you consider R1 has two directly connected networks, which is this one, which is the LAN, and we have the WAN. And if you take R2 also has two directly connected networks, which is its own LAN and the WAN. Now if you look at the routing table of R1 will have an entry saying that 172.168.1.0/24, which is this one, is connected to fast Ethernet 00, and in order to reach this network, hops means the number of routers, is 0 because it's directly connected. If a network is directly connected, number of hops required to reach that network will be 0. And also it has another information, 172.168.2.0, which is the WAN, is connected to serial S000, and again as a directly connected network, so the hop count will be 0. But you can see at the moment R1 does not know anything about the LAN of R2, which is 172.168.3.0, because in order to reach 172.168.3.0 you need to go through R2 and then reach. So what happens is R1 periodically will send this routing table to R2. So R2 will compare its routing table with the one that you got. Now we should have look at R2's routing table. It should have 172.168.2.0, which is right here, connected to serial 000, which is a hop count of 0, and there should be 172.168.3.0, which is this one. Interface is fast Ethernet interface, let's say, fast Ethernet, and hop count should be 0. So these are the two items that you have in the R2 directly connected. But when you get the update from the R1, now it contains a new entry. When you compare R2's routing table with the R1's routing table, new entry 172.168.1.0, which was there, right, can be seen. So what happens is, this will R2 will update his routing table with the new entry saying that 172.168.1.0.24 is connected to, well, if you want to go there you have to go through serial 000, isn't it? So serial 000, the hop count becomes 1, because if you want to reach 172.168.1.0 you need to go through R1. And after some time R2 will also send this update to R1, so R1 will update his routing table with 172.168.3.0, and again it will be same serial 000, hop count will be 1. So this is the process. This is how routers communicate with each other. Now if anyone in the LAN, let's call it LAN A, if anyone in the LAN A wants to communicate with LAN B, R2 knows where to forward, because R1 knows that LAN B is connected to R2, and if somebody in the LAN B wants to communicate with LAN A, R2 knows that LAN A is connected to R1, so it can forward because it has the routing information. So this is known as a routing table. Now, since there are many routing protocols, we need to be able to compare them. So how do you compare two routing protocols together? Now we discussed about 4, just to remind the routing protocols. I told you that we have RIP version 1 and 2, EIGRP, that is Interior Gateway Routing Protocol, and EIGRP, which is Enhanced Interior Routing Protocol. Now how do you compare between these 4? There are more protocols as well. How do you compare? Well, you compare based on a matrix. Now this is the matrix, the 4 points that is more important. Time to converge. Time to converge means, if you assume that the network is starting for the first time, you have communicated or you have configured the routing protocol, but this is the first time that you are starting all the routers. Now that means each router have to discuss with each other, and they need to be able to send this information. They need to be able to send these routing tables to each other. That takes some time, isn't it? So the time taken for the routers to completely understand all of their routing information or share all of their routing information is known as time to converge. So we are looking for a routing protocol where time to converge is lower, because if it is take long time for them to learn about these routers, within that time period there might be problems. And then scalability. Scalability means, can you use this routing protocol on a smaller network, or a medium network, or large network, or extreme large network? Or a routing protocol will be able to handle only small networks. So that's the scalability. How well, when the number of routers are increasing, when the routing protocol, how well will it behave? How well will it support the scalability? So we are looking for a routing protocol that should be scalable, isn't it? And the resource usage. When I say resource usage, routers, they do have a processor, CPU inside, and it has a RAM, non-volatile random access memory. So routing protocol will use a lot of resources. It's like a software which is running. If a routing protocol is using many resources of the router will be busy. So we need to be able to find a routing protocol that does not eat up or does not waste routers usage resources. So the low resource usage is something that we are looking in a routing protocol. And finally, you have to think about yourself as well, how easy or how difficult it is to implement this and maintain. Most of the routing protocols are basically straightforward to configure and maintain. However, some of them are difficult to maintain, some of the routing protocol. So if you are comparing a routing protocol, you need to be able to compare between these matrices. Okay, for example, let's say if you are comparing EIGRP with RIP, you need to have 3 columns. In the first column you have the attributes, for example, time to convergence. Second column RIP, third column EIGRP. So you write the time to converge, and then you put whether it's high or low, or what is the time to converge in RIP, and then you put what's the time, whether high or low, what's the value in RIP or EIGRP. And then the second point is scalability. Then you write the answer whether RIP is more scalable or whether EIGRP is more capable. Likewise, you can compare. So you can't just say one is better than the other without looking at this matrix points. But if you compare, if you highlight the distant vector routing protocols, I forgot to mention, even though we are talking about distant vector routing protocol, the other type which is not in your syllabus is known as link state routing protocols. So you have 2 types of routing protocols: distant vector, otherwise known as DV routing protocols, which you are going to discuss, we are discussing at the moment, and then link state. So distant vector is very simple. For example, RIP version 2, EIGRP and EIGRP are example for distant vector routing protocols. Very simple. But link state algorithms are a bit more complex than that. So example for link state routing protocols: BGP, ISIS, not the terrorist organization, okay, but ISIS, and OSPF. BGP stands for Border Gateway Protocol, by the way, and OSPF stands for Open Shortest Path First. Okay. Now we are talking about distant vector. So in common problems with distant vector, advantages. Usually all of these distant vector routing protocols are easy to implement and maintain, and they require very low resource requirement. They don't take much of your CPUs or other routers resources. Disadvantages: they are a bit slow, so they take long time to converge, that means to learn about each other, and they are pretty much used in small scale network. Scalability will be a problem. But the biggest problem of all, they are prone to something called the routing loops. Routing loop means where the packets are rotating, looping within a certain network without getting dropped. Now let's discuss how a routing protocol works. Now to discuss about this, we are using the the behavior of RIP. Now, even though we have 4 protocols in our syllabus, RIP version 2, EIGRP and EIGRP, to explain about the distant vector protocols, we are using RIP as example because it's a true distant vector routing protocol. Okay, now initial startup is known as a cold start. That means you're starting the network for the first time. So what happens is routers will learn about their directly connected networks. If you look at this diagram, router 1 routing table. So for router 1 there are 2 directly connected networks, which is one is this one, 10.1.1.0, and the second one is 10.2.00. so they put that information in the routing table along with the connected ones. Because they are directly connected, hop count will be 0. R2 at a cold start, it has again 2 directly connected networks, both of them are WANs. So that's 10.2.00 connected to serial 00. Hop count will be 0 because directly connected, and then 10.3.00 connected to serial 001. Hop count is 0 again. And then R3, we have serial 001 connected to 10.3.3.0 and faster than 0/0 connected to 10.4.00. So this is the initial network discovery. That means routers put their directly connected networks information into the routing table. And then what should happen? Each router start to discuss about or share in this routing table, their own routing table with each other. So this is how it works. R1 will share the routing table with R2, R2 will share the routing table with R1. So they compare the routing tables and update for any new information. So what happens is, after some time, all of them will have information about each other. Now if you look at these routing tables, R1 knows about 10.3.0, which is right here, and 10.4.0 right here, and the hop count is 2. Can you see that? Because if R1 wants to connect to 10.4.00, it should go from serial 00, then go to R2, that's 1, and then R3, that's 2, so hop count will be 2. So likewise, after the initial network exchange, they will be able to send this information to each other. So they have all the information about their networks in their routing tables. Let's see how the convergence is working. So even though we took this small example, when you have large number of routers, this process will take time. And the convergence time, if you can remember what we have discussed, convergence time means the time for all of these routers to learn about all of this network is known as convergence. So what we said, initially this time is little bit slower in RIP or in distant vector routing protocols in general. Okay, let's moving forward. Let's see how the table is maintained. So routing tables are maintained using 4 timers. RIP uses 4 timers to maintain these routing tables. The 4 timers are router update timer, router invalid timer, router hold down timer, and router flush timer. So let me explain how this works. Now router update timer means each router on a network will send their entire routing table to their neighbors every 30 seconds. So imagine that you have a couple of routers like this, 1, 2, 3, 4 and 5. Imagine they are connected also. So what happens is, each router, if this is R1, this is R2, so R1 will send the routing update every 30 seconds to R2, and R2 also will send this to R3 every 30 seconds and back to R1 as well. So likewise, each and every router will send their entire routing table every 30 seconds. router invalid time. So what happens is, imagine that you keep receiving this information every 30 seconds. That means R2 will get this update from R1 every 30 seconds. But suddenly you're not getting that message. So you're supposed to get a message, but you're not getting it. So what happens is R2 will wait. It will wait another 30 seconds. Still you're not getting the message. It will wait another 30 seconds. Still you're not getting the message. That means you missed 3 consecutive route updates, right? It should send route update every 30 seconds, but R1 failed to send this 3 times in a row. So when that happens, R2 will assume that R1 is dead. R1 is not working properly, and it will cross out that information from the routing table. It will not remove it from the routing table, but it will put it as temporarily down. And also R2 will inform that to the neighbor, saying that okay, look here, R1 is down temporarily, so don't send any messages which are going to R1 because it's down. So if you think about the invalid timer, then 3 consecutive route updates means 3 into 30, because we know the route update is 30 seconds, so that becomes 90 seconds. That's the router invalid time. And then router flush timer. Now imagine that after even 90 seconds you don't hear from R1 and you still wait. Well, 120 seconds, 150 seconds, 180 seconds, likewise for 240 seconds. To 240 seconds you are not hearing from R1. Now R2 can only assume that R1 is completely dead, down. So what we'll do is, after 240 seconds, R2 will remove the entry of R1 from the routing table. It will remove R1 as a working one and inform the other neighbors, saying that okay, R1 is completely down, there's nothing called R1 anymore, remove it from your routing table. So this is what known as the flush time. Right. Now to hold down time. After 240 seconds, after R2 remove it from the routing table, you suddenly hear from R1 again, you're getting update. Now for the problem is, R2 can't trust R1. It might be a delayed message, it might be a long old message. So R2 will not update the routing table yet, it will wait. Imagine that R1 is again sending a message in 30 seconds, because it should, isn't it? If it is R1 is working every 30 seconds, it should send message. So you're getting the second message also. In the 60th second, you're getting the second message also. R2 will still wait until without updating the routing table. Now you're getting third one also. So 90 seconds also, you're getting the third one. Now R2 can believe that R1 is really back. Okay, and it will put it to the routing table and update the other network, saying that okay, R1 is back, you can send messages. So that is known as the hold down timer. So the timer for the hold down time is again 3 into 30 seconds, which basically means 90 seconds. So hopefully you are clear about the 4 timers. So I have given more details about this route update timer, invalid timer, flush timer and hold down timer. So you can read about them. I will leave this video for 1 second. So you can see route update timer. I have given you that, saying that it's 30 seconds. Pause this video when you're going through it and read the information. And invalid time I have given as 90 seconds. And router flush time I have given as 240 seconds. And hold down timer I have given as 3 consecutive route updates. So 3 consecutive route updates means 90 seconds. Update that information. Okay. Even though RIP works like this, EIGRP has a very different mechanism. EIGRP actually is known as a hybrid protocol. Hybrid means it's a mix of distant vector routing protocols like RIP, and it shares some of the qualities of the link state algorithms such as BGP and OSPF. So the problem with RIP is that because it waits for a long time to verify whether the link is down and wait 30 seconds before sending update, it is slow. So EIGRP does not wait 30 seconds. It will only update whenever something changes on the network, rather than waiting 30 seconds. If there's any change, for example link going up and down or link is down, immediately it will inform to the party. And it doesn't send the entire routing table. What happens is basically it will send only that particular update. Okay, those are known as triggered updates. So that's the main difference between RIP and EIGRP. So you can see in the diagram, when this 10.4.00 is down, EIGRP will immediately inform R2 saying that okay, 10.4.00 is down, unreachable. R3 will inform that to R2, and R2 will immediately say that to R1 saying that okay, 10.4.00 is unreachable, and same way it will inform R1. So it's immediate. So a condition which can trigger an update is known as, it can be one of these. It can be interface change state, router becomes unreachable, or route is placed in a routing table, new entry, new network joins into R2. What happens? Well, R2 have to inform that immediately to R3 and R1 saying that okay, new network is connected. So EIGRP is faster in this method because it shares some of the qualities of the distant vector and link state. So second part of this lecture will be continued next week, but I do have a homework for you, assignment. What you need to do is you need to compare link state routing protocols. Even though we are learning distant vector routing protocol, I want you to write a report, or rather compile basic information about BGP, that is Border Gateway Protocol, and OSPF, that is Open Shortest Path First. So what you need to do is you need to find information about BGP. For example, how does it work, where are we using it, is it for the larger networks or the smaller networks, and also same thing for the OSPF. So allocate like 300 words for each. For example, you can use 300, 250 to 300 words for the BGP, and again 250 to 300 words for the OSPF, and put that information as a comment in the forum. So you'll be getting marks for it. Okay, make sure that you put that in your forum. So what you need to do is, again I will repeat, you need to find information about BGP and OSPF, two link state routing protocols, using 250 to 300 words each. So we'll see you again with the second part of this lecture, and hopefully you can go through it and resolve any problems. If you have any questions regarding the lecture, please feel free to update the forum in the Q&A section. Thank you.